Alright, I'm Phil, and we'll be talking about sulfur isotopes with the atom probe in the script that we wrote to do that. Mostly I'll be talking about pyrite, which is an important mineral in ore deposits. We use the sulfur isotopes to determine the source of the ore fluids, among other things. The problem analytically is that it's a very complicated mass spectrum. Lots of different elements are present here beyond just Fe and S. There's lots of molecular peaks as well, and we're looking for really small differences in the sulfur isotopes. This is the sample we were trying to do this with in the first place. It's from Nevada. It's a gold deposit, and the gold is actually hosted in this arsenic-rich overgrowth on the arsenic-poor pyrite core here. You can see that's really fine oscillatory zoning. We wanted to see the difference between, number one, the core and the rim in terms of the sulfur isotopes, but really if there's any differences between all of these different growth zones in these sulfur isotopes. This was something that was done about 10 years ago with the nanosims, and so they found relative differences, but they weren't able to do this quantitatively. Again, we're looking at the third and the fourth decimal place, so it's analytically quite difficult. For us, it's an overlap problem. Every place that we try to look at a sulfur peak family, there's some sort of an overlap. Most of these problems we can't actually solve. On the main 32 to 36 peaks, there's the double sulfur which overlaps, which is just too difficult to solve. At the S2 peaks, though, we have a shot at it. The problem then becomes there's 4 sulfur isotopes, and there's different combinations of those isotopes that can give us the peaks between 64 and 70 Daltons. So how do we go about this? So the first thing that we do is we use Jesse's code to very systematically determine the area under the peaks and get a single value of counts at the 64 through 68 peaks. Then we use those numbers and we start making guesses. We tried doing linearly least squared. We tried a couple different ways to solve this overlap problem, but in the end we settled on this sort of brute force approach, which is really just we make a guess, we start with the natural abundance, and we just populate 2 rows with the abundances of those guesses. So literally just the number 32, 33, 34, and 36 in row 1 and row 2, the same isotopic numbers in row 1 and row 2, and we randomly pull from row 1 and row 2, we combine it into row 3, which simulates the random combination of the atoms as they're coming off the tip to form our molecules. So we then have a simulated mass spectrum in row 3 here, and we can compare that to the real mass spectrum. We can calculate a mismatch number for that guess, and then we go to town. So we use the natural abundance as sort of the starting point, but we go left, right, up, down, every single way we can think of in terms of iterating the 32, 33, 34, 36 sulfur isotopes to we start guessing and guessing and guessing and doing a grid search of guesses. At each grid point, we have a mismatch, and we have then a 4D sulfur isotope space. Here everything's plotted to 34, so we can actually show it on a 3D plot. And then we end up having the red is more mismatch and the blue is less mismatch. So the intersection of these mismatch planes is our best guess, which is what our code spits out. And then we can actually use our code on real data. So we started off with some simulated data from Andy, where he started with a known number of sulfur isotopes, and we were able to match that quite closely. We used similar samples to what the nanosims study looked at, and we saw the same heavy, light relative differences. We published a paper on that, which is really nice. We also could look at the arsenic peaks, which the ASS peaks are shifted to a clean part of the mass spectrum, and we can compare to see if the double S peaks gives us the same answer as the ASS peaks. And not all of our data sets have arsenic, so to be consistent, we use the double S peak for everything. After that, we really went to town with some reference materials, and we ran them all sorts of ways that we could think of on all the instruments that we have available at Oxford, and then in the end, were able to get a fairly good deviation from the nominal values, which are in the top row there. This comes with a big caveat, is that we had to do a lot of scratching our heads in terms of the instrumental artifacts. So there's a very specific set of conditions that gives us the right answer, 80 picojoules. We've only managed to get it to work on the XR. There's a very specific voltage range over which this works. And how we define the grid search also seems to have a bit of an influence on the numbers that are put out, sort of whether it's an even or an odd number of bins, and whether we end up on a local minimum there. The first paper on that is what came out last year, which is presenting the code, but only really for the relative differences. We've done a lot more work now, and hopefully the next paper will be out this year, hopefully, where we'll also release the code then with that. It'll probably be in microscopy and microanalysis. Thank you for your time.
I have a question about your running conditions. Do you think that the running conditions you've chosen are correct, or is it just that two wrongs make a right?
Well, our run conditions were we tried everything that we could think of, and where we got the right answer with the reference materials, that's where we settled on.
Okay.
It's not really the right way of doing it, but we were able to reproduce the analyses a number of times. So we're pretty confident that for some reason these conditions seem to work. Not 100% sure yet why. It probably has to do something with multi-hits. And we're still scratching our heads about that. But at the moment, we seem to be able to get the right answer. We seem to be able to do this consistently, and that's really what matters for us.
Great. There's a question from Dan. I think this is with his software development hat on. What do you think the main sort of areas for software development are for people working on geological specimens?
I mean, for us, the big thing is being able to look at chemistry very carefully, and isotopes are something that geologists are very interested in, looking at isotopes on the nanoscale. This is something that the guys at Curtin have done. This is our foray into this using sulfur isotopes, and very specific systems seem to work and others don't. And I don't want to talk about the lead stuff. That's Steve Reddy's and the other guy's domain. But I think isotopes and being able to do something proper with that is really where it's at.
Okay, great. We have a question. What is the minimum amount of sulfur required in the material for the approach that you presented to work? Would it also work for sulfur impurities in alloys, or is that too low of a concentration?
That's a great question. So at the moment, we've only really tested it with pyrite. We're not even looking at other sulfides. So FeS2, so that's 66 atomic percent sulfur. That's where we're comfortable with it. Mm-hmm. As soon as you start getting other elemental impurities, we start worrying about other overlaps maybe. For now, it's a very niche. It's a very niche thing. Pyrite is a very important mineral, which is why we're doing it. I wouldn't be that comfortable putting it outside of this little comfort zone yet.
Okay. I think we do have a little bit of time. We have a break, but I'm gonna be cheeky and ask another question. Put you on the spot while we've got you. How many multiple hits? What detected multiple hit fraction did you have in these analyses?
I can't remember off the top of my head now. It wasn't that small of a number though. We're working a little bit with Kamika. TyPros was starting to do some work for us before COVID. So we haven't managed to get any analyses done yet at Kamika with their instruments. But the multi-hit is something that they're looking at more than we are.
Okay.
Again.
Great. So it's always something I'm interested in. So just briefly to mention, you mentioned Jesse's peak fitting. I thought it'd be worthwhile just to explain for people. This is a slide that he sent me. He's using a MATLAB toolbox that was, I think, originally developed for X-ray peak analysis. But it's, I think, a general peak fitting tool. And he's been using this to quantify the counts from peaks. And so I believe Phil's been using this code. So just to put that up there and mention that's what they've been doing. Okay, so we've been going for a little while. I think it'd be great if we all just take a 5-minute break